major issue is connectivity. At my site, unfortunately, this is first time. So, very good morning to the main coordinator of this event, uh, ATAL Online Faculty Development Program, uh, Dr. Mohammed Sajid, Assistant Professor, Department of Computer Science, AMU Aligarh. So, thank you all for giving me this opportunity to deliver this talk on large scale machine learning algorithms. So outline of this talk will be introduction to support vector machine. This is one of the most important tool of machine learning for classification and then regression, clustering and all. So I would like to discuss this in detail. What are the linear and nonlinear cases and some advanced model of it, and then large scale kind of model. How to develop uh, a model for the large scale data, big data. So, what are the issues in the baseline models, and how can we improve those models? So, this overall talk will be based on the basics and advanced models. So, we'll cover both. So, I hope that who are just starting in the career of machine learning, so they will also be very, very helpful. So my starting lecture will be based on the initial basic fundamental of this SVM, which is one of the most important tool of machine learning. So this talk will be focused on a classification only. So support vector machine being computationally powerful tool for supervised learning, widely used for classification problem. In 1995 by Vapnik and all the regression problems. And it has several applications. I mentioned few, particle identification, pattern recognition, bioinformatics, but nowadays in all the direction like prediction, disease diagnosis, like early diagnosis of epilepsy, early diagnosis of Parkinson, Alzheimer, or forecasting, remote sensing. So, and all biological sciences, usually mathematicians, computer science people are used, and that physics usually for the research. So and negative samples. So if you see this example, so it shows two different kind of classes. So you can see two different dots, bold and the circle kind of dots. So the basic idea how to classify such kind of data. Okay. So you can see that in the middle, I draw a line. So using this line, we can classify this kind of data. Okay. So I can draw another line. So classify data with another line. So I can see another line, and there are several such lines that can classify. Okay. So the basic idea is to find out a upper plane. So how to do that? Vector machine for so which is nothing but maximize the margin. So and sometimes happens that at the time of this line, so we see classification. So once the misclassification coming, some error is coming, and misclassification means here if the data point appear in different class, okay, in different site. So or so the is nothing but the distance between these two points from the data point of each we are getting this margin, and margin is very far from both the right. So this is one of what we had to do is automatic, right?
Sir, we can't hear anything. Voice is not there.
Yes, there is some issue at speaker's end, and we are informing him. Please be patient.
Hello. वॉइस ऑफ है. या कैन यू हियर मी नाउ? ओके. So you can see that you can see in this formulation. Dr. Sajid, can you hear me?
So we can hear, but you have to share your slide, sir.
Tanvir sir, we can hear you clearly, but you have not shared your screen. That's why we cannot see anything. So you need to share that once again.
So could you please see this screen?
Now, yes, sir, we can see that. We can see that. So can you go 1 2 slides before that, because the voice was breaking at that time.
This one?
Or 2 3 slides before as well, sir.
This
Yeah.
one?
Yes. Somewhere.
Okay. Okay. Yeah, sorry for the interruption. A lot of issues today. I don't understand the reason. So, this is nothing but I was discussing about if there is any misclassification in classifying the data. So we just push them with one error. So if there are more than one data point which are misclassified, so we put in the objective function, we have to minimize this error. So we'll show it later. So, but we have to penalize such misclassification, such error. So, maximizing the margin is the first property, as I mentioned in the last these slides, that we are trying to find out a decision hyperplane, which hyperplane is best, which hyperplane is the optimal hyperplane. So the first property of SVM is coming that maximizing the margin. So what is maximizing the margin? So margin is nothing but it is the distance between these two supporting hyperplane corresponding to class +1 and -1. So why we are saying this support vectors? Because support vectors are those vectors which lie on this supporting hyperplanes. So you can see that only 3 data points are there. So what happens? Only these vectors are important. So other training samples are ignorable after that. So once we got it, so this is these vectors are important vectors to decide the main hyperplane. This is an hyperplane. So you can see the mathematical interpretation of this maximizing the margin concept. We have this supporting hyperplane, just a simple equation, W dot x plus b equal to 1. Sometimes I'm writing W transpose x plus b or W dot x plus b. Both are same mathematically. Okay. So the middle one is the decision hyperplane, W dot x plus b equal to 0, and supporting hyperplane corresponding to class +1 and -1. So we are taking the distance between these two. So so it is called margin. So it is coming 2 upon norm of W. So to maximize this margin, essentially we have to minimize W. Okay. So to minimize W is equivalent to minimize norm of W square. So you can see here that we are minimizing 1 upon 2 W transpose W plus capital C summation xi k. K is running from 1 to some R. Okay, so here we are adding this xi. These are misclassification error term or called slack variable. So just minimize. Yes.
ಇಲ್ಲ ಲೈಸೆನ್ಸ್
Any question?
ಐತೆ ಹೆಲ್ಮೆಟ್ ಇದೆ
Yeah,
No,
please
sir,
mute
I
your
think
mic.
there is some
Please
voice
mute your
problem.
mic. Yeah.
You continue, sir.
So here C is nothing but as a parameter though to control the overfitting issues, and xi here are the slack variables. So this is a very simple formulation. Almost all the people, whatever doing in machine learning, basic machine learning, all are using as a toolbox. So here I'm trying to discuss the foundation basics of this toolboxes. because this is one of the well-known tool of machine learning for classification, for regression, for clustering, for multi-class classification. So you can see that there are two kind of formulation: hard margin, soft margin. So hard margin is that when we are talking about simply linear SVM, there is no misclassification, there is no error term. So very clean data. And another formulation is for those noisy data. So whatever misclassification is coming up, so we also minimize those misclassification. We take the sum of all those and then minimize. And with the parameter C, C is can be viewed as a way to control the overfitting. So one important note while solving this dual, I'll explain in detail about this the concept, how this dual is coming up. So, but here one important note, that the data point appearing in the dual formulation in the form of inner product. You can see that xi transpose xj. So this is essentially nothing but, you can say, dot product or inner product, dot product in vectors. Okay. So it will help us to understand the nonlinear concept. This is a very simple formulation so far for the linear case. So you can see this example. We have very simple data where we have red dot and blue dot. Okay, and you can see that we can classify this data nicely. We just draw a line between red and blue and we can classify. There is no problem. It is a case of linear classifier, and it works nicely. But what happens if we talk about the second example? We have red dots, blue and red. So how to classify this kind of data? So linearly it is difficult. In R, it is difficult to draw any line to classify this kind of data. So what happens, what we are doing, and I hope that you will understand the motivation or concept of this SVM moving ahead towards nonlinear with this example. So what happens in the second example, in R, in the real line, we cannot draw any line that classify red and blue dot. But if we slightly move ahead, R means real line to plane, or you can take a function fx equal to x square, means R2. So it will go in the parabolic shape. So data point will move upside, and then you can see that we can draw this line and we can classify this kind of data also. We can draw this kind of data in R2, not in the real line. Okay. So it will depend on the data sets, what data is given to us. Sometimes it happens that the data is linearly separable in 2 dimensions, and it may not be linearly separable in R2 and 2 dimension. It may be linearly separable in high dimension. You can see this complex example. So in this case, you can see that the original this input data, whatever data, this red dots or blue dots. So if we cannot find any line, we cannot draw any line to classify such kind of data. But we can map this data to some high dimensional space, not R2, but in some high dimensional space. I'm using word sum, right? You see the previous example, we map that data in R2 in plane, okay, and we classify. But this is a highly complex data. It may be, you can see even more complex data after that. But we map this data in some high dimensional space where the data are linearly separable. So you can see we are mapping with some function phi, where you can see that in some dimension this data is coming out to be linearly separable. Now the question is coming, what is phi? What is the nature of phi? What is the definition of phi? So in support vector machine, we do not even know about the nature of phi. So here the the working style of phi is just to map the data, given data in some high dimensional space. So how it will work, we'll discuss now. So what happens in the nonlinear case when we are trying to get the dual formulation? So in place of this xi transpose xj, so in the nonlinear case you will see later on that the dual formulation appears in the form of phi x transpose phi x. So here phi xi transpose phi xj, these are also nothing but real number, inner product, right? So when real number is coming, so we do not even know, we do not need to know about the nature of phi when we are simply getting a real number. Okay, so this is the advantage that we are working in a very high dimensional space, but kind of linearly. So this is a great advantage of SVM. We discussed two things. One is maximizing the margin, and second we discuss kernel trick, this non-linear trick, how to handle non-linear data. So you can see this one small example of two-dimensional k equal to 1 plus xy transpose xj square. So whatever you we elaborate more, and we can always write in the form of phi xi transpose phi xij. So, and where phi x is represented in this manner. So whatever we have given, we can always write in this form, in the form of inner product. So there are several kernel functions available in the literature. So few of them are available here. I just show linear kernel, polynomial kernel, Gaussian kernel, sigmoidal kernel, and several kernels are available in the literature. If you are interested, you can go through some book of machine learning to get more information about the kernel functions. So you will see that kernel function is play an important role, and it looks very difficult to decide that which hyperplane to use, which hyperplane not to use. So this is again a question. So you can see here that dual formulation for the nonlinear case is coming phi kxi xj. Here kxi xj is nothing but it is represented in the form of phi xi transpose phi xj for the nonlinear case, for high dimensional space. Okay. So this overview, SVM locate a separating hyperplane in a feature space and classify points in that space. And it doesn't need to represent the space explicitly, simply by defining a kernel function. And here kernel function plays a role of dot product in the feature space, high dimensional space. So this is, we have seen those advantages so far. So far I discussed geometrical interpretation and little bit description. So now in the next few slides, I would like to focus how to, if we have given formulation of SVM, means an optimization problem, how to solve it. So I would discuss first a more general way of solving an optimization problem, and then we'll discuss one of the SVM formulation in detail. So I hope that will motivate you to work in this direction rather than just using the toolboxes. So let us consider a training set corresponding to class 1 and -1. And here xi's are the input. And obviously this the second, this y1, y2, yl are the outputs. And here we are considering a two-class problem. So it could be -1 or +1. Okay, and essentially we are looking for the separating hyperplane or decision hyperplane W transpose x plus b equal to 0 between positive and negative hyperplane. Means hyperplane corresponding class 1 and -1. So, so the middle one will be the separating hyperplane, exactly in the middle. And data point which lie in the planes are termed as support vectors. Support vectors, I already have discussed those vectors which decide the decision hyperplanes. Okay, so this is more clear picture for better understanding of support vector machines, that the middle one, we just take the difference between w dot x plus b equal to 1 and w dot x plus b equal to -1. So it is coming out to be 2 upon norm of w, and we have to maximize this margin. For example, if a student are sitting in a class, and in a class girls and boys are sitting, okay, and we just see the best separation of boys and girls. So what we can do, that we can take the more distance from boys with girls. So we can say that best separation. So if they are very close, so it could not be the best separation. You can draw a line in the middle, but could not be the better separation. So better separation will be the more distance between these two. So it means that essentially here the concept is we have to maximize this distance between these two classes. So these class could be men and boys and girls. It could be color, right? A red and blue color. So it could be in several ways. So I would discuss only this problem for more discussion. I already have discussed this, already shown this picture. So I would discuss this formulation in detail, how to solve it, okay, how to find out its dual formulation. So before going ahead for solving this formulation, I would discuss the basic understanding of an optimization problem. So let us consider one function fx, minimize fx subject to the constant gx equal to 0. It means that if somebody asks you a question that how to minimize, how to maximize a function subject to some conditions, some, like here condition is given gx equal to 0, another function. So how to solve it? It's a very simple question, anyone can ask. So the necessary condition for x naught to be a solution of this optimization problem such that partial order derivative of this function plus alpha times gx, it should be 0 at x equal to x0 or x naught, and constant is as it is gx equal to 0. Here alpha is Lagrangian multiplier. So if there are multiple constant, more than one constant, so the only difference while solving it, we just add these constant like alpha 1 g1x plus alpha 2 g2x plus and so on alpha m gmx, depending on the number of constant. Rest is same. Okay. So what happens if we have the same objective function and we have inequality constraints like gix is less than or equal to 0? So how to get the solution of constant optimization problem?
So how to solve it? We just take the partial order derivative of this, and the constants are seen gix is less than or equal to 0. Okay, so here fx plus summation alpha I gix, this usually called Lagrangian function. And then later on we set gradient to 0 and take the partial order derivative with respect to w, b, whatever is given in the Lagrangian function. So now, as I mentioned that my focus now is to get the dual of this formulation. How to do that? So first we need to write the Lagrangian of this problem. So how to write the Lagrangian? Objective function as it is, and plus minus this alpha and this constraint. So we are writing exactly the same thing here, and this another beta I also mentioned corresponding xi I, because xi I here it is given greater than or equal to 0. This one. So this is the way of solving the dual formulation of the standard support vector machine. Then we take the partial order derivative with respect to w, b, xi, alpha, beta, and put again there, and we got this formulation. And you can observe that this is coming xi transpose xi. So here it is nothing but data points in the dual formulation are nothing but in the inner product or dot product. Okay. So as long as we calculate the inner product in high dimensional space, if we talk about nonlinear case, so we do not explicitly those 5. So what happens? So let me show for the nonlinear case, it is coming in this way: phi xi transpose phi xi. So this is the only difference is coming up. So in case of any question, you can stop me, I can answer you. Otherwise, we can talk after the lecture. Okay. So these are some standard drawback in the standard SVM, that training is relatively easy. No local optima unlike a neural network, and it scales relatively well to high dimensional data. And trade-off between classifier complexity and error can be controlled explicitly. Some drawback, as I mentioned earlier, that we need to choose a good kernel function. So I already mentioned few kernel functions in the literature, and people are using multiple kernel or ensemble kernel. Computational complexity of SVM is a bit high, and SVM with hinge loss is sensitive to both label and feature noise. So my next slides, it will be based on these issues to resolve the issues of computational complexity, to resolve the issues of this hinge sensitivity towards noise. Okay. So the first problem is based on tuned support vector machine. This is recent, means introduced just around 13 years ago, but it is one of the efficient model of SVM because of the computational efficient, and its efficiency is more than standard SVM. So we'll discuss classification using two non-parallel hyperplanes instead of single hyperplane, as in the case of conventional support vector machines. So let's consider a binary classification problem to classify data points belonging to class +1 and -1. It's presented by matrices A and B corresponding to class +1 and B corresponding to class -1. And here L1 and L2 data points belonging to class +1 and -1 respectively. So if you remember the formulation of SVM discussed in the previous slides, what we observe in SVM that we have one objective function subject to the constraints of both the classes. In here in this formulation, what we see that we have two objective function in 2 and 3, equation 2 and 3, two objective function and two inequality constraints. So here in equation 2, first term is nothing but the sum of square distance of data point class 1. Okay, and second term is the sum of error term, misclassification, and C1 and C2 are the parameters. Okay, and subject to the constraints means the data point should be like I mentioned, the objective function. Essential objective is of 2 that the data point should be very close to class plus 1 and it should be far from the other class, that is class B, that is class minus 1. Okay, means idea is coming proximality, proximal SVM concept, so and non-parallel concept. So one point is in this case we are assuming that in case of SVM, what we see that we have parallel supporting hyperplane. So in SVM, those issues are relaxed, and we say that let it be non-parallel. Okay, and each hyperplane is close to the data point of one class and far from the data point of other class. It's a kind of proximality corresponding to classes 1 and minus 1. So what happens if we talk about complexity? So in support vector machine, what we see that we are solving a very large single quadratic programming problem. So here computation complexity is coming big O m cube. So m here, let us assume that m is the number of training data points, right? So and if we see in Tune SVM, let us consider that the data point corresponding to class 1 as half and half for the other class. So it means that if I talk about the complexity of Tune SVM, so it will be m by 2 and 2 times m by 2 cube. So m cube upon 2 times m by 2 cube. So it is coming out to be approximately 4 times faster than SVM. So if you see the numerical experiment, sometimes it is 20 times, 30 times faster, 100 times faster, depending on the data. Right. So you see the dual formulation in the same manner we discussed in the previous formulations in 4 and 5. You can see that the matrices appear in the dual formulation may not be invertible all the time. We are writing H transpose H and G transpose G whole inverse. So these matrices may not be invertible all the time. So we need to add extra regularization term manually like delta to avoid this ill conditioning for calculation of these matrices, inverse of the matrices. So these are some issues in the algorithm and people resolve will show that formulation also. And then we solve W corresponding to class 1 and minus 1. Okay. And another issue with this formulation that maximizing the margin concept is somehow not available. So those issues are resolved in this formulation. This paper came after 4 years in 2011 by Shao et al. In IEEE transactions neural network called the Tune bounded support vector. So it's an improved version of Tune SVM, the last algorithm. They incorporate structural risk minimization principle. Okay? Means they introduce the concept of maximizing the margin in Tune SVM. by introducing extra regularization term in both the objective functions. Okay. And another contribution is that they present another efficient way of solving called SOR technique, successive over relaxation. This is an iterative approach and takes less time, so more efficient than TMSPM. So if you see in 9 and 10, so essential difference only in the first term of both 9 and 10. Rest are same. So, but doing this, you can see 11 and 12 dual formulation. It is theoretically more better, theoretically more advanced. You can see that C3I and C4I in the previous algorithm we were adding manually, and it is coming automatically, right? And C3 and C4 are parameter, and we can tune by taking the range of these parameters, and we can get the best best parameter to get the best accuracy. So performance will be better. Okay. So now I would discuss least square formulation of tune support vector machines. So in the least square SVM, if you know, some of you obviously know who are doing in machine learning or SVM, that support vector machine, if you compare with least square version, is extremely fast than SVM. The main issue is that we are simply solving system of linear equations rather than solving quadratic programming problem. So we, these people, Kumar and Gopal, in expert system with applications, they resolve this issue for Team SVM and propose least square version. And this algorithm is extremely fast and simple. That again solve system of linear equations. So, and you can see it's very simple. Idea is quite simple, but the outcome is really nice. You can see that in 18 and 19, the only changes what they did in 18 and 19, they just replace inequality with the equality in both the constraints. And in objective function, you can see that they just change one norm with the two norm. So these two small changes, they did it, and they are simply directly solving the problem in 20 and 21. So in this case, I hope that some of you may understand that how researchers are changes in the development in the existing formulations and giving a new idea. So these are very small change, but they are changes the nature of the problem. So for those things, you need to understand individual papers, the concept. So only then you can go. So you can see that least square tune SVM completely solve the classification problem with just two matrix inverses. So in the previous algorithm, what we were doing, we were taking the inverse, we were solving the quadratic programming problem. So, but in this case, we just need to solve two small matrices. And this is the decision function. I could not show the decision function, but these are standard decision functions in almost all the classifiers. So one can extend the same for the nonlinear case by introducing phi, and the only change in the dual formulation, in the place of xi transpose x, it will be phi xi transpose phi x. Okay. Now I would go for another formulation, which is so far efficient algorithm, robust energy based least square tune SVM. So what happens in this formulation and with the previous formulations? So in this formulation, what we are doing in each hyperplane, we are introducing an energy parameter. An energy parameter, we are just taking the range of the parameter. So this is one of the great advantage of this formulation, and one is least square sense. I already told that least square is one of the fast algorithm, simply solving system of linear equations. So those essence are there, and the third that we are introducing extra regularization term. So to make this concept of invertibility issues in the dual formulation, those also resolved. Okay. So simply make the least square sense by introducing extra regularization term and introducing energy parameter for each hyperplane. So idea is great. So you can refer these papers. This paper and codes are publicly available. You can go through my homepage and you can get these codes and paper both. So finally we are getting this solution. So now I would show the advantage of this formulation. What happens in 2014, 6 years ago, one paper came in Journal of Machine Learning Research. Um, do we need more than 100 classifier, over 100 classifier? So it was a genuine case that which classifier to use, which classifier don't use, which one is better. So there are several classifiers available in the literature. And finally, they conclude that random forest is the rank 1 classifier. So it is a 2014 paper. Okay. So in one of my discussion with PM Sugandhan in 2016, 2017, during his visit in IT Indore, so we discussed that can we see, we already developed several models based on TuneSVM. Can we see where our TuneSVM model exists? So we got a surprising and interesting result. So you can see that we have taken all the models, whatever given in that 2014 paper, do we need over 100 classifier, exactly same data sets, same platform. You can see all codes are publicly available. So you can see that the rank 1 classifier is called RELS-TSVM. So it is a rank 1 classifier in the literature. So you can see that RELS-TSVM is proposed in 2016 by us, and we did the comprehensive evaluation of these models in population 2019 in applied soft computing. So it concludes that this RELS-TSVM is a rank 1 classifier. So if any of you are working in classification, so you can also consider this classifier, and it uses is usually gives a better result when compared with other baseline models. Large scale data. What happens in all the previous models I discussed so far today? So whatever be the nature, either it's least square or TBSVM, means improved version, theoretically advanced model, whatever. But in all the previous model need to calculate the inverse of the matrices. So what happens due to calculation of inverse matrices, it results in the high computational complexity. And thus, such models are not suitable for the large scale data. So now we recently developed a model which overcome these shortcomings. Means the model can efficiently handle the large scale data, and even in the formulation this invertibility issues are nowhere. You can see this is a very simple formulation. You can see, and it recently accepted in ACM transactions on internet technology. So this is one of my students, Shilpa Sharma, MSc thesis student, who developed this idea. So you can see in 1 and 2, the idea is quite simple, but the way of solving is great. So what we are doing that in 1 and 2, we are taking in the Lagrangian function both the constants, both the equality constant. So while solving the Lagrangian functions. Okay, and then we are getting the KKT condition by taking the partial ordered derivative with respect to W1, B1, eta 1, alpha, beta, and all. Okay, and we are finally getting this W1 and B1 solution, direct solution. It's a least square sense. You can see that in the 9 that there is no issue of the invertibility. Invertibility issues automatically resolve the way of solving this problem. Okay, and you can see that the dual formulation of this, it is coming up in the form of this, and here Q cap is this matrix, and you can see in this matrix also there is no issue of the matrices, invertibility of the matrices. Okay, and in the same cap is appearing in 11, so you can see that we are simply solving unconstant minimization problem and do not need to complete the inverse of the matrices. Okay, so I'm not discussing this more advanced thing, may not be good for you. Okay, so you can see the results of this formulation, TBSVM, least square TBSVM, and TBSVM, more theoretically advanced, and this larger scale model. And in this table, you can see that I consider only a small size of data. So in a small size of data, you can also see that results are performing better when compared with the baseline models. Right? And here also some more data. And this is for no linear data. So it's performing better, right? But the essence of this model is for the large scale. Whether the model is applicable for the large scale data or not, so you can see these results for the large scale data. So you can see the size of the data up to 1,30,064, and you can see that the last column, which is called the proposing idea for the large scale data, it is working fine except the baseline models. They stop after some iterations. So you can see that this model is performing better for the large scale data. Okay, you can see more results on another synthetic data, NDC, generating this data. So you can see that after 45K, TBSVM and TuneSVM stopped working, and after 50,000, RELS TSVM stopped working. But this large scale algorithm working fine. And if you compare with the time, like you can compare NDC 50K data, and first two baseline model stopped working, and RELS TSVM takes time 4,612 seconds, but large scale model takes just 253 seconds. So you can just see this. So overall, you can see that if one is looking for the large scale model, one can refer to this model. codes are publicly available. One can go through my GitHub repository. You just check my homepage, you will get it. GitHub repository. Okay, and this is the effect of parameters on accuracy of linear model. So what happens? There are several parameters in the optimization problem. So now, what is the role of this C1, C2, C3, C4 and accuracy? So you can see that when we are slightly changed C1, C2, C3, C4, then accuracy varies. So once accuracy vary, so it means that we have to very carefully choose the parameters. So in all models, we usually prefer to use some method like grid search, means k-fold cross validation, to find out the optimality of this parameter, best parameters. Another example of another data set. So here, large scale data set doesn't need to compute the inverse of the matrices. And dual formulation is an unconstrained optimization problem, which can efficiently solve using SMO technique. And the SMO is fast and efficient model, can give better results with less time complexity. Dr. Sajid, could you please let me know whether time is available so that I can explain more in another 10 to 15 minutes?
Yes, sir. We have 10 to 15 more minutes.
Okay, thank you. Thank you. So, so the one issue is resolved. That's computational complexity. Now, quickly, I'll discuss the issue of noise. So, here we are discussing first time in Tune SVM, original Tune SVM, we are introducing pinball loss function. A pinball loss property is that it is insensitive towards noise, right? So you can see in 4 and 5, and you can compare with the original Tune SVM. I can explain you in 4 the second constant, that is minus b w plus e2 b plus minus xi1 upon tau 2 less than or equal to e2. So any student having background until 12th mathematics can understand this. So you can see that once this tau 2 goes towards 0, so here this xi1, it is nothing but it will be greater than or equal to 0. Okay. Similarly in 5, if tau 1 goes towards 0, so then this xi2, it will automatically reach to xi2 greater than or equal to 0. So essentially what happens in 4 and 5, they reduce to the original formulation if tau 1 and tau 2 goes towards 0. So, and we are stopping the issues of noises using this constraint, stopping with this tau 1 and tau 2. So more properties, more advantages, more theoretical foundations are available in this paper. You can see journal Tune Support Vector Machine with Pinball Loss Function, 2019 paper. So, and we can get this solution. So, and after that, one of my 2 students, this Rahul Chaudhary and Sanchit Jalan, so they introduced its sparse version. So noise issues resolved in the first paper, and in the second one, that sparsity issues also resolved. So when the data is not sparse, and how to develop such kind of model to make more sparsity. So these 2 models are more efficient. Please go through this paper. And this BTech student got the best IT indoor award for this paper. So you can see the results. I just show ranking criteria, not experiments, due to limitation of slides, timing, and all. So for more information, please go through the paper. So average rank is better, means lower is better, and higher is not good. Means rank 1 is better always, and rank 2 is next, rank 3 is next to 2, like this. So 2.35 is better than the all baseline models. Okay, almost this technical content almost over. Now I would like to discuss some research activities going in my research lab. So some of you may be interested. You can see that some research projects are going on in my lab. So these are research project. Like first is it's machine learning, means we need to develop a novel machine learning approach for the early diagnosis of Alzheimer's disease. Um, so this is under Ramanujan's team. Second is optimization models and algorithm for non-parallel SVM under Early Career Research Award scheme. The third is detection of human brain disorders. So human brain disorder kind of overlapping with the first one, but the focus is epilepsy. The third project, only epileptic patients we are working on using by developing machine learning approach. And this fourth one is more focused on EEG signal data. So it is epilepsy, but this is more focused with the EEG signals. So it is from Data Science Research Initiative of DST ICPS scheme. And the fifth one is digital forensic knowledge integration and intelligence. So it is also going on MHRD Spark scheme, and few more projects also going on. I could not mention those. So if any of you are interested to work in any of these projects, you are welcome. Drop an email to me. So email are already available in the first page. I can show it to you later. So I would like to acknowledge research funding agencies who have supported me to execute my research ideas. And now I would like to invite you to submit your new work. If you are working in the theme of these special issues, the first is applied soft computing elsewhere. So portal is still open. Last date is over, but it's still open for submission. If you would like to submit, you can submit. If your work is matched with the theme of this special issue. Another is open until December 31st. We are going to extend further. Robust data analysis and its application, and also ORS. Both are most prestigious journal. So, and I would like to invite you to the international conference we are organizing this time in Sri Lanka, Machine Intelligence and Signal Processing. So you are also welcome to submit your high quality papers in the theme of this conference. And now, particularly, it will be really very helpful for all the participants. If you are interested in computational intelligence, machine learning, then please join this summer school. Very soon, I will share with all of you the details. So this event will organize November 26 to 29, and highly most of the people speakers are IEEE fellows. So highly great personalities in this school. So this is one of the most prestigious event in India. So once in a year, organized by IEEE CIS funding. So this time we are organizing at IIT Indore. So please, you can join this event. And these are some short-term courses we are organizing here at IIT Indore. One is next week, 5 to 10 November at IIT Indore. This is on artificial intelligence driving biomedical data for disease diagnosis. And second from in next month, December, next to next month, December 18 to 20, recent trends in machine learning and soft computing. So it's done from my side. So now floor is open for questions. Thank you so much for attention, and really very sorry for the late due to uh, connecting issues. Uh,
Uh,
so my
so
email,
there is a question from my side. Can
yeah,
I?
yeah, please.
Yeah. Sir, I was saying that in your discussion you also compare various algorithms,
Hmm.
and you mentioned the paper in which random forest was considered the best one, and in
Hmm.
another paper you have proved that the algorithm that you have devised is performing better. Sir, can we make general claims about what is better or not, or we should always see that from the perspective of data on which we are running?
Yes, 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 yes. I think what happens, I have given very less information here. More information are available in the paper. What happens? Let me explain. In 2014 papers, so they did really excellent job. It was very tedious task for doing such kind of experiment. It took maybe 2 years to do that kind of work. So they finally conclude that random forest is the best classifier. So what we did in and what we conclude in our paper, 2019 paper, so we have considered tune SVM based model only for two class classification, binary classification problem. Okay, and we consider around 8 TuneSVM based models, and then we compare with all those 2014 papers, and we conclude that these models are also better. One can look for these models also. So it was very difficult means to do the similar kind of work again for TuneSVM base. One can look for, but what we did in that paper, we are just focusing only binary classifier, two class classifier, and we only for 8 models with all those previous whatever they have included. So it was the idea that using those, you comparing with those models and considering only binary class models. So we have done that. So there are kind of ideas they have given, but we have chosen only binary because we are working on binary class classification. So using that, we conclude that this variant is also better, not even better, but best than random forest also for the two class classification.
Okay, sir. Thank you.
Is
So,
that okay,
yeah, sir,
Dr. Nadeem?
definitely. Yeah. Okay. Thank you, sir.
Hmm.
Because we have already
Hmm.
seen, I mean, this, they also consider some, they always do research with some kind of assumptions beforehand before making any claim. So that's why I want to clarify. So now I'm satisfied with that. So all the participants, thank you all of you for your patience. There was some problem initially, but all of you waited for that. Thanks for all of you. Still, if you have some questions, you can put that into the chat box. I will ask sir to give answers of those questions, if any. So no questions. So thank you, Dr. Mohammed Tanveer, for giving us your valuable time. And you faced some problem initially. You were not able to join, but you kept on trying, and we are really grateful that you made it convenient to give a lecture on our FDP organized by Department of Computer Science, AMU Aligarh. And you are doing a tremendous job. Your research is excellent. In fact, you took some time out of your busy schedule. You are involved in various projects, various conferences, various summer schools. We can understand you are so busy, but still you gave us some of your valuable time. So thank you very much, and hopefully we will coordinate with you again in future workshops, webinars, and FDPs as well. Thank you, sir, once again.
Okay, thank you so much to everyone, participants, organizers, whole team. Thank you. Thank you so much.
So all the participants, you are requested, you can leave now, and the next session will start at 12 noon as shown in the schedule before. Thank you, everyone.